Okay, so the first point that should be made is that everybody has done modular arithmetic. Even people who don't realize it, even people who don't really do much math, they know modular arithmetic, because if I tell you that it's 11 o'clock right now, and I ask you, what time will it be 4 hours from now, you probably won't say 15 o'clock. You'll probably say, oh, it'll be 3 o'clock. And that's because, well, you take 11 plus 4, you get 15. But then you realize that's the same as 3. And what we mean by the same is those two numbers, 15 and 3, they are not literally the same number, but they are equivalent numbers in the world of mod 12. So what modular arithmetic does is it essentially glues together a bunch of numbers that originally were different numbers and makes them all sort of one object. So, for example, if I do, let me just take an easy one, if I do mod 6, okay, then basically what that would mean is, well actually, yeah, okay, so mod 6 is fine. So that would mean that basically we're going to say that 1 and 7 and 13 and 19 and 25 and 31 and 37 and so on, all of these numbers, and you can do negative numbers as well. Okay, so all of those numbers are basically the same. They literally aren't the same, but we view them as being the same. Sometimes people will do things like this. They'll put brackets around the numbers, and what that means, and they might put the little n down here to emphasize what the modulus is. It just means that, basically what it means is that when you subtract the two numbers, so in other words, if you subtract any two of these numbers from each other, it doesn't even matter which ones they are, it is divisible by n. And that's just another way of saying n divides a minus b. And this is a notation that you may not have seen before, but that's very standard in Math 302. So you'll need to be getting used to that notation. So, for example, take any two numbers in this list here, and if you subtract them, you're going to get something that is a multiple of 6.
Okay.
So it just means that some multiple of n is equal to that number. So 15 and 3, if you subtract them, you get something that is a multiple of 12. So they are the same in the world of mod 12.
Cool.
Okay. So all of these numbers get glued together and viewed as one giant set. In Math 302 and Math 407, it would be called a coset. Is the word for it. It's started out as a bunch of different separate numbers, and now it gets thought of as a single object that has all of these numbers sort of glued together as one. So they're all really the same. And then another set of numbers that would all get glued together would be these. Okay, so that's a second element in the set. Okay, that's a second. We call these congruence classes.
Okay.
So far I've drawn 2 congruence classes on the board, right? Let me just erase this part right here for a moment. The next, another example of a congruence class here would be this one. 2, 8, 14, 20, 26, and so on. And it goes both ways. Okay, so that's another congruence class. Okay, there's another one, which would be 3, 9, 15, 21, 27, 33, 39, and then negative 3, negative 9, negative 15, okay.
Goes to 5.
And then there's, yeah, yeah, so the next one would be 4, 10, 16, 22, 28, and so on.
Okay.
I'm actually going to write them all out. Okay, and then the last one would be has 5 in it, 11, 17, 23, 29, 35, 41, and so on. And -1, -7, and so on. Okay, so every single integer is in one of those 6 places. And so this first set becomes, you know, the congruence class of 1 modulo 6. This set is 0. This set is 2. This one is 3. This one is 4. And this one is 5.
Okay.
But then if I ask you, well, there's a lot of other numbers. Yeah, there are, but if I ask you where's 6, the point is it's actually the same as that. And this one is the same as 7.
Right.
This one's the same as 8. So you're just lumping them together and saying that they're all equivalent. Okay. So you probably know this notation. So this is a set of integers. So if we want to talk about congruence classes, we will write that as this notation. So z sub n, and what that is, very simple, it's just all of these congruence classes. So there are actually going to be a total of n of them there. So in this example, it would go from 0 to 5. Okay, so they're all listed there, and you just basically do wrap-around arithmetic. So wrap-around arithmetic just means that if I add, let me just pick an example here. If I want to add, I don't know, 2 to 5, I add those together and I get 7, but then 7 can be reduced to 1. So I could say that 2 plus 5 is equal to 1 in this context. Just like with clock arithmetic, 11 plus 4 is equal to 3. So that's basically all we're saying. And it turns out it doesn't matter, like if you add 2 and 5 together, you'll end up here, right?
Yeah.
But if instead of 2 you chose any other number along this line, let's say you chose this number instead, and instead of 5 you chose any other number along this line, let's say you chose this number instead, if you added the 2 square numbers instead of the 2 circled numbers, right, 26 plus -7 is 19, you would still end up in the same row. So, in other words, it doesn't matter which, because remember, it makes sense, these are all the same, so it doesn't matter which one you use to do the arithmetic with. Okay, now, in another notation for saying that 2 congruence classes are equal. So this just means, I already said this before, it just means that n divides a minus b. But another way of writing the notation is to write a is congruent to b mod n. So we almost try to make you believe that they are the same number. We just use this slightly changed equal sign. So a doesn't literally equal b, but it is congruent to b in the world of mod n. Really just means that they are in the same congruence class. So basically what you get then is you get this giant picture of z that is then broken up into all of these congruence classes like that. Okay, so that's the first basic thing about modular arithmetic. Modular, and by the way, in my book, which is on the Combinatorics website, one of the chapters is called Number Theory. It's chapter 4. So, and one of the sections within Chapter 4 is Modular Arithmetic. So, and it's written for a high school level. So it's you'd be able to read it, I think, and not have too much trouble understanding it.
Okay.
So that's another place you can look for a simple explanation on some things. Okay, so let me see, where are we at here? So this structure Zn actually forms what's called a group or a ring under addition and multiplication. So you can, just so you know, you can. So this is sort of the algebra piece of this, is that you can take two congruences and you can add them together. And the way you would do that is you just take the individual numbers and add them together and then build the congruence class out of that. So this is how addition works. Okay. Now, you have to be a little bit careful to make sure that that is a good definition.
Okay.
What I mean by that is, what if somebody else came along and found another number that was the same in congruence land as 8. So suppose these are the same, and suppose these are the same.
Okay.
So these are equal, this is equal to this, and this is equal to this. Then we do the addition using the same formula. Then it better be true that this is equal to this.
Right.
Well, this being equal to this just means that n divides a minus a prime. This being equal to this just means that n divides b minus b prime. In other words, a minus a prime is some multiple of n.
Okay.
And b minus b prime is some multiple of n. Then the question is it going to be true? Is it well defined in the sense is it really equal to this? Because if it's not, then we have a problem, because our addition would depend on which of the, in that long list of numbers, would depend on which one we chose. And if one person chose one of them and another person chose another one, they come back at the end of the day with different answers, and that's confusing. So you can't do that. So you would need this to be true. What does that mean? That means n needs to divide, so this is the question, does n divide a plus b minus a prime plus b prime? In other words, is this a multiple of n? Well, but you can look at it. So a plus b minus a prime plus b prime can be reorganized as a minus a prime plus b minus b prime, right? Which is nx plus ny, which is n times x plus y, right? And since x and y are integers, x plus y is an integer, so this is an integer multiple of n that equals this difference. So this implies that a plus b has the same congruence class as a prime plus b prime. This is what's called check, and you're going to need to know this, and you're going to see this again in your other classes too. This is check. This basically means that addition is well defined.
Okay.
Addition is well defined. That's really what that's saying. Okay. Obviously, subtraction is pretty much the same as addition.
Right.
That doesn't really affect anything. So we can do addition, we can do subtraction, and then there's also multiplication. And luckily, multiplication also works in a very natural way.
Okay.
There's the definition of multiplication. You can take that as a definition. And again, if somebody else came along with a prime and b prime and multiplied them together and got a prime, b prime, with respect to congruence classes, it won't matter. They'll get the same answer. Okay. Now, you do have to be a little careful. So, careful with division. And let me give you an example. Okay, so in the world of mod 6, 10 would be congruent to 4.
Okay.
Again, all this means is that if you go back to the lists that we wrote earlier, in that list, the 10 and the 4 were in the same set.
If you switch the 10 and the 4, would that carry a different meaning?
Nope. These mean the same thing.
Okay.
Doesn't matter, actually. The point is, if you subtract these numbers from each other, you get a multiple of 6. Okay? So that is true. However, if you divide, you say, oh, I'll divide both sides by 2, you would get 5 congruent to 2 mod 6, and that is not true. Turns out what you can do, as far as division goes, is you can divide including through by the, if you also divide through by the mod, then it does work. Then it does work.
Oh, okay.
Okay, so mod 3, it does work. Okay. With me?
Yeah.
Okay, so I don't know how much of all of this, I mean, this is already would take a long time in a paper just to explain this background.
Right.
You might not want to go into all this stuff with well-defined, I mean, your professor would be impressed, I think, if you did go into all that, but that's going to take you time to write all that up. Okay, so let's get on to another problem.
Okay.
If we want to solve ax equals b for x, alright, so in the real number system, we can do this provided a is not 0, and we would just get x equals b over a. So it doesn't work out so nicely if we want to solve this in Zn. Things are more difficult. Okay, this is not this simple.
Okay.
Because this looks like a fraction, and again, just to remind you, in Zn I don't have any fractions. All I have are these numbers, these congruence classes. Every single thing I write down has to be in that congruence class.
Right.
Of course, the way you get this x value is that you you find an inverse for a. You find something that you can multiply by a that will cancel it out, which in the case of the real numbers is simple. It's just the reciprocal.
Right.
So you multiply. So instead of thinking of this as dividing by a, you can kind of think of it as you multiplied both sides by 1 over a. But we don't have reciprocals here. So like, what is the reciprocal of, so back to Z6 again, if I ask you, what's the reciprocal of that, right, well, there is no 1/2, so the answer to what this is, it has to be one of these 6 things, and it has to be something that you would multiply 2 by that would give you 1. Just in the same way that a times 1 over a gives you 1. So why do we multiply this through by the reciprocal? It's because a times 1 over a is 1, which means that the coefficient gets canceled and you isolate x. So we have to talk about inverses in Zn. Okay. So to solve, I'm just going to, actually, let me write it using my other notation because that's going to be more standard. To solve for x in this congruence equation, right? We would like to quote unquote cancel the a. You'd like to cancel the a from both sides.
Right.
And the fact of the matter is you can't always do that. Okay. So let me tell you exactly when you can do it.
Okay.
You can do this if and only if you can cancel the a if and only if the GCD, do you know what that means?
Greatest common divisor.
Right. The greatest common divisor of a with n is equal to 1. In other words, the two numbers have to be relatively prime. That's what that's called. So if and only if a is relatively prime to n. So for example, trying to find a reciprocal for 2 in the world of mod 6 does not exist because 2 is not relatively prime to 6. Have you seen this before? Any of this?
I've seen it in notes or a textbook or something. But
Okay.
I just didn't understand it at the time.
Okay.
I've seen
Are
it.
things making sense so far?
Yeah.
Okay. Have you seen the Euclidean algorithm?
I have. That's familiar. I think I saw it.
Okay, so let's say, okay, the basic idea is that if a is relatively prime to n, then you can come up with a reciprocal for a and use it to cancel and solve for x.
Okay.
So
That's what the Euclidean algorithm says?
the Euclidean algorithm is actually a process for for finding what is the quote unquote, it's not really a reciprocal,
Yeah.
but the congruence class that cancels out the congruence class of A. That's really what this Euclidean algorithm does. So let me just give you, let's take a specific example. Let's suppose I wanted to solve 77x is congruent to 10 modulo 100. I'll just pick a nice number like that. So I believe 77 and 100 are relatively prime.
Okay.
So what you basically do is the following thing. You take 100 and you divide it into 77. So I'm basically going through the division algorithm, the Euclidean algorithm with you.
Okay.
We're not even really getting yet, it's 4:15. Not quite getting yet to the guts of what you need for the proof of the Fermat's little theorem and stuff. Because that's what you're supposed to do, right?
Yeah.
Okay, so we'll get to that probably not in this lesson, but at least you'll be able to start working on this background, and then we can have a second talk or something.
Sure.
So 100, you just divide it by 77, and you get a remainder of whatever, 23.
Okay.
Okay, so then you take the previous divisor. Have you seen this?
Mm-hmm.
Put it over here, and divide that into 23, and it goes in there, I believe, 3 times. So 3 times 23, which is 69. And then to that you would add 8.
Okay, yeah, I've seen this.
Okay, so then you take the 23, you put it here. It goes into 8 2 times with a remainder of 7.
And then divide by
8 goes in 1 time with a remainder of 1. The last non-zero remainder that you get is the GCD of the two numbers. So, I mean, the next step would have been 7 divided by 1. It goes 7 times with a remainder of 0. So
Okay.
this last number is the I mean, we already knew just by thinking about the prime factors
Right.
that 77, which is 7 times 11, does not have any common factors with 100, which is 2 squared times 5 squared. So I can see just based on the factorizations, these two numbers would have been relatively prime. But this Euclidean algorithm takes it a step further for us and allows us to,
Always find
well, yeah, I mean, because I don't want to give an answer, I don't want to tell you that x is 10 over 77. Because there is no 10 over 77 in the world of mod 100. I have to give you a number that's between 0 and 99 with those brackets around it.
Yep.
Okay, so what this algorithm then allows you to do is work backwards.
Okay.
Have you seen the going backwards part?
No, I don't think so.
Okay, so what you do, you have to do the math very carefully here, but you start with 1 and you write 1 as 8 minus 7. So you solve for the GCD, 8 minus 7.
Okay.
Then you take the 7, you're going to work your way back up. You take the 7 and you rewrite that as 23 minus 2 times 8. And before you go back to the previous line and go any further, it's good to put the 8s together. So I'm going to simplify. There's an 8 there, and there's 2 more 8s. That's 3 times 8 minus 23.
Okay.
And of course, that does still equal 1. With me?
Yeah.
Okay, then you take the 8, you go back to the previous line, and you write that as 77 minus 3 times 23, and then minus 23. And then again, you're going to simplify it again. Let's simplify this thing one more time. So you simplify this thing again, and you're going to get 3 times 77 minus 10 times 23.
Okay.
And that's because there's 9 factors of 23, and then 1 more there. And they're all being subtracted. Then I take the 23, so 3 times 77 minus 10 times, I take 23 and I write it as 100 minus 77. And now this becomes 13 times 77 minus 10 times 100.
I see.
I'm assuming I did that all right. I went fairly quickly. So this becomes an equation. And this is the important fact. And I'm teaching this to you because you're going to see, not just for the paper. You may not put all this in your paper, but I told you if you want to take my class next semester, there's some brushing up, some basic stuff, and this is part of it. So
Okay.
the basic fact is that if you take the GCD of two numbers A and B, it can be written via the above process as an integer combination of A and B. So in other words, GCD of A and B can be written in the form A times M plus B times N, where A and B, I'm sorry, where M and N are integers. And the proof of this fact really is just this, what we just went through right here. It just shows you, so the GCD is the last non-zero remainder. In this example it was 1. And we have written it as an integer combination of the two numbers that we started with. These are playing the role of the A and the B, and the M and the N are the 13 and the 10. Now, why is this equation so important? Well, it's because you can take this equation, and if it's true that these two numbers are equal, then it's still true after I put brackets around everything. In other words, if two numbers are literally equal, then when you think about which of the congruence classes they're in, well, obviously they're in the same class because they're the same number.
Yeah.
So, in other words, in Z100, 1 is the same thing as, and we can use the fact that multiplication and addition and subtraction, we respect all of these brackets.